Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome back to the nanoHUB-U course, Thermal Energy at the Nanoscale. We're in the middle of week 5, talking about carrier scattering and transmission. And today we're going to talk about boundary and defect scattering, which we're lumping these two things together because generally they're similar, at least in some respects. The way that the carriers react to boundaries and internal defects is similar. So I'll start by reminding you what we did last time. We talked about essentially a simple scattering model and a transmission model for thermal conductivity in the Landauer framework. And what we did there is we pulled the mean free path, that's lambda, out of the integral. And when we did that, we showed that generally speaking, that the form of the thermal conductivity expression is similar to what we found for kinetic theory. So that gives us a little bit of, I hope, gives a little bit of confidence that we're on the right track. But one thing that happened when we did that is that we had a very simple model for the mean free path, and we're going to start to build up into some more complex models this week. So phonon scattering is actually very complicated in general. We're going to talk mainly about two types. We'll talk today a little bit about elastic scattering by boundaries and lattice imperfections, if you can think of a boundary as a lattice imperfection. And generally, those will be single carrier types of scattering events. So I'm interested in how the carrier is moving, what its energy is, its direction before the scattering event and after. It's the same carrier in both cases. And generally speaking, that this is going to be happening when we have defects, which could be atoms that are in the lattice that shouldn't be, or maybe they should be, but they're not part of the large scale crystal structure. Dislocations and grain boundaries and physical boundaries of the envelope of the material. In this case, in all cases that we will study, energy is conserved because that's the first law of thermodynamics. And then whether momentum is conserved, it depends on whether you're looking at the particle or the particle and the lattice together, kind of the background. But then moving on to phonon scattering, that's the second type. We won't talk about that today, but it's quite a bit more complicated and has some nuances. There's a couple of different types. One of those is called a normal process in which both energy and momentum of all the phonons are conserved. And then there's something called Umklapp or U processes, where energy is conserved. As I said before, it better be. We have a law for that. But that something odd happens to the phonon momentum. We'll talk about that in the next lecture. Today, we're going to look at boundary scattering. And when we do this, we'll see that we'll draw a picture. We're interested in heat flow in a particular direction. So whenever you have a size effect, you really have to start considering the direction of heat flow that you're interested in, because the material will almost always be anisotropic or have anisotropic properties if we have boundary effects. So in this case, this is a very intuitive approach for boundary scattering. Our intuition, I hope, would tell us that the scattering rate will be simply the velocity, that's how fast the particle is moving, divided by some length that's confining that carrier. And so a lot of people have studied this. There's quite a bit of literature out there. But generally speaking, we want to make some average length scale. And the best one, the one that's most common at least, is this capital L that we're showing here. And capital L is just sort of an averaging of a cross-section through which the heat is flowing. A characteristic length of that cross-section, I should say. And then, we are engineers, so there's often a fitting parameter. That's the capital F. And there are a lot of other things that could happen with boundary scattering, but generally speaking, this is the first order approach for understanding, for modeling. It's a velocity divided by some characteristic length scale. Now, another thing that happens, so the surface roughness can be very important in the effect of boundary scattering. And so here, if we have a rough surface, that means everything is relative to the wavelength of the carrier. But if we have a rough surface, that's what we're showing on the top here, then we have very small wavelengths relative to the surface roughness. And in this case, what can happen is that a boundary, I'll circle something here, this boundary, in that case, will turn the momentum of the carrier around. And so that will impede heat flow substantially, whereas the one, if let's say that we were interested in heat flow from the left to the right, the scattering event over here looks more or less how we would, like a mirror reflection. So that's called a specular reflection. And if the wavelength is much smaller than the characteristic roughness of the boundary, then you're going to get a mixture of these things, and you'll actually impede heat flow quite substantially. However, if we have a smooth surface down in the bottom, the carriers generally, I'll start here, the carriers generally, if they have a very long wavelength relative to surface roughness, they will come in and bounce off, and they'll maintain more or less their momentum in the direction of interest here. That is the direction that is parallel to the boundary. And so we have less impedance to heat flow, or resistance, I should say, to heat flow. And in this case, then, if we have smooth boundaries, then generally speaking, we'll have higher thermal conductivity. The other kind of a elastic scattering event, single carrier elastic scattering event that we'll talk about today is that of a lattice imperfection. So this is, as I said before, a situation where you might have a substitution of a foreign atom into a lattice site, or we could also have an interstitial atom that's placed in the middle of the lattice. But the main thing that happens in either case is that it changes our spring constants. It also changes the mass of the lattice site, of the atom at the lattice site. And so what we do, again, this is, as you might expect, it can be quite complicated, but generally speaking, what we do is we say that this defect inside the lattice will have an effective radius or diameter of influence around itself. And so when a carrier moves past it, then that radius of influence or diameter of influence will be manifest in some kind of a scattering event. And again, we're going to see that there's actually a frequency or wavelength dependence to that phenomenon as well, just as we saw in the rough or smooth boundaries in the last slide. So I want to talk a little bit about a very simple collision model. Let's say that I had a region, a defect region with a diameter of d here. That's what we're showing on top. And I form a cylinder in my material. And I'll just look down that cylinder and I'll say I'll kind of put other defects along the way according to the density of those defects, which is something generally we can measure. And we're interested in transport from left to right. So we're interested in transport going in this direction. And what we'd like to do is to say, well, if those defects were fixed in space, which is really what we're talking about here, they're not moving around themselves, we'd like to understand how frequently the carrier will scatter, or how far it will move between scattering events. And so this is just simple logic here. If we know the number concentration of these defects, that's n sub I, then I want to count the number of scatterers in a cylinder of length L, and that's shown in just below here. So I know those two things. This is just some fairly straightforward logic. Then I can say that my average distance between scattering events will be the length of this cylinder divided by the number of scatterers that are inside the cylinder. It's very simple. And then when we do that, we find a very easy relationship, a very straightforward relationship, where the mean free path is inversely proportional to the number concentration of scatterers. That's kind of hopefully fits our intuition. And to the cross section of this cylindrical tube. That's pi times d squared, where here d is serving the role of a radius of that tube. If I wanted to express this in terms of scattering rate, the scattering rate is simply the velocity, the group velocity of the carrier, divided by the mean free path that we just derived. And then we find that the scattering rate is simply proportional to the number concentration, this pi d squared, which we'll call a cross section, a scattering cross section, and the velocity. So if we make a little bit more general, you'll often see, if you study scattering, you'll see it written almost like we had before, but again, there often arises a need to make some engineering approximation. So we'll put a term alpha that's a constant, often used to fit data like thermal conductivity, for example, and then we have again our n sub I is our defect concentration. That's per unit volume. Sigma is a scattering cross section, and that's how you'll see it tabulated. In general, in lots of different kinds of scattering events, you'll see scattering cross section and meters squared cited instead of, say, a scattering diameter or radius, d from the last page. So the scattering cross section is really kind of how big the defect looks to a certain type of carrier. And in fact, it's not just a certain type, but a certain carrier. So some carriers, let's say, that have very long wavelengths might not really see an object that's very small ever, even if it can kind of pass right through it. And that's another thing that we need to add to our analysis here. And so we'll just talk about one of those types. This is Rayleigh scattering, which is a well-known concept in the study of electromagnetic radiation and transport and photon transport. But generally speaking, we're interested here in looking at and considering the case when the wavelength, this carrier wavelength, is much, much larger than the size of the defect. That's that d that we talked about before. And if we have a really long wavelength relative to the size d, then essentially the wave is virtually unaffected. But as the wavelength becomes smaller, or the frequency becomes higher, then you start to see the defect more and more. And this is a very well-studied problem. It's called Rayleigh scattering. And you can see that it's actually been modeled for defects in which you have a host, a host material, and then you have a defect. So the defect introduces a mass discontinuity. So there's an impurity mass, and that's what the difference between the impurities mass and the host atom's mass is delta m. M is the mass of the host atom. The rest of this is pretty straightforward. The only thing that's somewhat new is this capital V. That's the primitive cell volume, because again, that's really a factor in the spatial size of the defect. But the most important thing to realize, and this is the classical signature result from Rayleigh scattering, is that the scattering rate goes as frequency to the fourth power. So you can see it's a very, very, very strong dependency on energy. So these longer wavelength carriers, the scattering rate is very small. But as the wavelength decreases and frequency increases, you can see that the scattering rate changes very, very rapidly. All right, so that's it for today.